Good morning, my dear students. My name is Dr. KCH Apparao, working as a associate professor in Mechanical Engineering Department. Today we will discuss analytical questions or critical analytical questions uh, in question bank, which are prepared in question bank. Mainly topic on the conduction process. So, what are the different critical thinking questions on conduction? We'll see first of all. So, the first one, we derived the one-dimensional steady-state conduction equation in the case of the slabs. In last class, we already discussed the uh, Cartesian coordinate system, derive the dimensional steady state equation in Cartesian coordinate system we discussed, and steady state conduction equation in cylindrical coordinate system for the cylinders. For spheres also we already discussed on. So based upon the previous equation, that is steady state uh, conduction equation in Cartesian coordinate system, we know that formula which one already derived in previous class, and d square t by dx square plus d square t by dy square plus d square t by dz square plus q by k is equal to 1 by alpha. Alpha is the diffusivity, dou t or dt by d small t. So this is the formula we derived in previous class also. Alpha is equal to k by rho Cp. So thermal conductivity, density, and specific heat. You know this one. So this is the formula for deriving one-dimensional steady-state conduction. One-dimensional source. Uh, just we are considering the any one direction, either it is in x direction or in y direction or z direction. So if you consider this one, so that shows the x direction differential equation or heat conduction equation. If you consider this one differential equation in y direction, if you consider this one differential equation or steady state conduction equation in z direction, if you consider this is the steady state condition, then it will be 0. Then the formula will be like this one. So this is equal to 0. Okay. So if you consider if you consider the internal energy is negligible, if you neglect the internal energy, then it will be also 0. Then the formula is equal to del square T is equal to 0. So that is the formula, you know this one. Dou square at d square T by dx square plus d square T by dy square plus d square T by dz square is equal to 0. It means d square T by dx square is equal to 0. D square T by dy square is equal to 0. And d square T by dz square is equal to 0. So if you consider any one direction, means if you consider x direction, you have to take this one. If you consider y direction, you have to take this one. If you consider z direction, you have to take this one. So by using this one, here I am considering in x direction, it means one direction steady state conduction. So for this one, we are taking just d square t by dx square is equal to 0, this formula. By using this differential equation or conduction equation, you can derive the one-dimensional steady state equation for the slabs. So here already given the equations, you can observe here also. So this is the equation what was we derived in previous class, the heat conduction equation in Cartesian coordinate system. Okay. So if you consider this Q, it means Q by K. If you consider this is a homogeneous body, Kx is equal to Ky is equal to Kz, you know this one. If you take K is the common, then the formula will be like this one. Okay, anyhow, if you consider, if you neglect the internal heat energy, this will be 0. If you consider this is the steady state condition, this will be 0. The formula will be like this one. Then, so if it is 0, total is equal to 0 means each term is equal to 0. Then kx dou square t by dou x square is 0. Then dou square t by dou x square is equal to 0. By using this one, you can derive the one-dimensional steady state conduction equation. Okay, for this one, integral both sides. dt by dx is equal to c1. Okay. Again, if you integral dt is equal to c1 dx, if you integral both sides, you will get equation, the general equation t is equal to tx t1 c1x c1x plus c2, general heat conduction equation, general equation. This is the, you know this one. By using this one, you can derive the uh, one-dimensional steady state conduction equation. So here, just we are considering one slab. The inner temperature, the one side temperature is equal to T1, another side temperature is equal to T2. Use the rate of heat transfer passing through this homogeneous body. Okay, so up to certain length x distance, just you are taking the temperature T. You have to find out this one. And boundary conditions x is equal to 0. At x is equal to 0, temperature is equal to T1. At x is equal to L, so length, thickness of this slab is equal to L. Temperature is equal to T2. So boundary conditions here at x is equal to 0. So temperature T is equal to T1. At x is equal to L, so temperature T is equal to T2. So by using these boundary conditions, we can derive the temperature T. Okay. So first of all, apply the first boundary condition in T is equal to C1x plus C2. Then we will get the formulas like this one here. You can observe here also. Okay. So we are taking this one. This is the, if you integrate both sides, you will get this general equation. So if you apply the first boundary condition, so that is C1 T1 is equal to C1 of x is equal to 0 means so we can substitute the 0. Then based upon the first boundary condition, T1 is equal to C2. Then apply the second boundary condition. What is the second boundary condition? That x is equal to L, T is equal to T2. If you apply the second boundary condition, then T2 is equal to, this is the formula, we will get this one. If you substitute that C2 is equal to T1, then C1 is equal to T2 minus T1 by L. Okay. Then temperature equation, that is T is equal to C1x plus C2. If you substitute the C1 value and C2 values, we know this one, then the formula is equal to like this one. So T is equal to T1 minus T2 by L into X. Okay. You know that rate of heat transfer based upon the Fourier's law, Q is equal to minus K into dt by dx. Okay, so based upon the Fourier's law. So here dt by dx, it means derivative of temperature with respect to x. If you derivative this one dt by with respect to x, then we will get the value. That is, the value is equal to T1 minus T2 by L. Okay, with respect to x. So substitute this value here. It means here this is the minus of, okay, minus into minus plus, then K into T1 minus T2 by L. So the final formula, it means one-dimensional steady state conduction equation in the slab is equal to T1 minus T2 by K by Ka, L by Ka. So this is the formula. Otherwise, you can write like this one: Q is equal to Ka into T1 minus T2 by L. Okay. So this is the formula. So by using this formula, you can solve the different numericals also. Okay. Next, we will see the composite valves. So here just we are assuming three layers of the walls or slabs are there. The first layer thickness, that is the LA. Second layer is the LB. Third layer thickness is equal to LC. Thermal conductivity Ka and Kb and Kc. Okay. So here a hot fluid is there. This is the atmospheric condition. So from heat heat is transferred from the hot fluid to atmospheric um, temperature in atmosphere. So this is the Ta. Ta is the temperature inside temperature, that is the hot fluid temperature. Tb is the uh, ambient fluid. So ambient temperature of the fluid, it means outer temperature. So heat is transferred from Ta to Tb. You know this one, from hot fluid to inner surface temperature means through convection process it will be heat will be transmitted and heat will be transferred. So here also from last surface T4 to Tb means here also convection process. So convection process, it means heat transfer takes place from the fluid to solid, that is by convection process. Solid to solid means by conduction process. So here convection process, here also convection process. In the first plate we will see the conduction process. In second plate, in third plate also we will see the conduction process. So finally R1 is the conduction, R2 is the conduction thermal resistance, R3 is the thermal resistance of the conduction. So Ra, inner surface thermal resistance by of convection process. Rb is the thermal resistance of the convection process for outer surface or ambient thermal resistance. So we'll see these temperatures. If you consider this one, suppose heat transfer, you know that according to Fourier's law, Q is equal to just HA into temperature difference Ta minus T1. Okay. So hot fluid temperature He, H suffix A, you can take like this one. Okay. Otherwise, if you consider the heat flux U by A is equal to H suffix A into Ta minus T1. Then you can write like this, and Ta minus T1 is equal to Q by A, Q by A into, so 1 by HA, 1 by HA. So this is the first two. So through convection process, the first equation, it means heat transfer from Ta to T1, then T1 to T2. So T1 to T2 means that it is a conduction. So you know the formula of conduction. So Q is equal to Ka into temperature T1 minus T2 by LA. So LA is the first plate thickness. Okay. Ka is the thermal conductivity. Okay. So then temperature, if you write like this one, T1 minus T2 is equal to Q by A, Q by A into Q by A into, it means otherwise 1 by LA by K, LA by K. So this is the thermal resistance of this one. Okay, in this way, just like here, temperature T1 is equal to T2, T1 minus T2 is equal to Q by A into 1 by LA by Ka. Similarly, T2 minus T3 is equal to Q by A into 1 by LB by Kb. Similarly, so T3 minus T4 is equal to Q by A into 1 by LB LC by Kc. So similarly, just a final T4 minus Tb is equal to, similar to this one, Q by A into 1 by Hb. Okay. So if you add this one, So minus T1 plus T1 will be cancelled, minus T2 plus T2 cancel, minus T3 plus T3 cancel, T4 cancel. So finally temperature difference is equal to Ta minus Tb by all this one. So the finally you will get this formula if you add this one. That is the uh, composite heat transfer, rate of heat transfer in the composite to slabs. The final formula will get, you can see here also. That is the formula is like this one, you can see here. Right? So this is the final formula. The final formula will be like this one, you can see. Okay, the final formula, that is if you add this one, all these values will be cancelled. T minus T2, this is the Ta minus Tb is equal to Q by A into all thermal resistances. Okay, so 1 by Ha, L1 by Ka, L2 by K2, L3 by K3. So this is the plate 1, plate 2, plate 3. Similarly you can add many plates. So the final formula will be like this one, you can, this is the final formula for the composite slabs. Q by A is equal to Ta minus Tb by 1 by Ha plus L1 by K1, L2 by K2, L3 by K3 plus 1 by H. So this is the formula. Okay, so in this way, just like we can solve the numericals based upon this formula. Next we will see derive one-dimensional steady-state conduction equation in the case of hollow cylinders. Previously the slab, so here cylinders. So here just like we are taking the inner radius of this cylinder is equal to Ri, outer radius is equal to R0. Okay, length of this cylinder is equal to L. Okay, inner temperature is equal to T naught, outer temperature is equal to not inner temperature is equal to Ti, outer temperature is equal to T naught. Okay, so if you consider the boundary conditions here, boundary conditions at R is equal to Ri, at R is equal to Ri, T is equal to temperature, T is equal to Ta. At R is equal to R naught, second boundary condition, T is equal to T naught. So this is by using this boundary condition, we can solve this one. In previous class also, we already discussed heat conduction equation in for the cylindrical objects. We already derived this one. So the formula is like this one. We already derived in previous class. So that is called. This is with respect to r and theta. So dou square T by dou r square plus 1 by r into dou T by dou r plus 1 by r square into dou square T by dou pi square. So here x and y variables will be changed. So this is related to x, this is related to y. So in z case, vertically that shows the same. There is no change in the vertical direction. So those were T by dou z square. See here, just like we are considering one dimensional. One dimensional means with respect to r. So no need to considering this angle phi r square. Just we can take this one. Those were T by dou r square plus 1 by r into dou T by dou r. We can rewrite like this one. This is so 1 by r dou T by dou r, derivative of d by dr of r into dt by dr. So we are rewrite like this one. Just if you derivative, if you integrate this one on both sides, you will get the general equation. That is the general equation is equal to, these are the boundary conditions, we know this one. Okay, general equation is like this one. So that general equation is equal to, this is the T is equal to C1 L LR, T is equal to C1 ln R plus C2. So this is the general equation. So by using these boundary conditions, if you apply the boundary conditions in this equation, you will get the temperature profile, temperature formula like this one. Okay, integral both sides, then we will get the C1 value like this one. Okay, so if you substitute the first boundary condition, second boundary condition, if you solve this one, you will get the C1 value. So C1 is equal to Ti minus T naught by ln Ri by R naught. Okay. So you know that formula. So C1 is equal to R into dt by dr, or C1 by R is equal to dt by dr. Okay, dt by dr. You know that Fourier's law, according to Fourier's law, Q is equal to minus K into dt by dr here. Okay, with respect to R. Okay, in this place you can substitute this value. It means dt by dr is equal to C1 by R. C1 is nothing but this one by R. If you substitute this one here, then we will get the rate of heat transfer. If you solve this one, then the Q is equal to like this one. Q is equal to minus Ki into dt by dr. dt by dr is nothing but C1 by R. Okay. If you substitute this value, we will get this formula. This is the one-dimensional conduction equation, one-dimensional steady-state conduction equation for the cylinders. Okay. So this is the value. You have to remember this. So similarly, we'll see these are the just composite cylinders. Just like here, we are taking the two layers. Similar to slab, we already derived that composite heat conduction in the composite slabs. Similar way, we can solve the uh, heat conduction in composite cylinders also, hollow cylinders. So the two layers, one is the layer A and the layer B. Inner temperature is equal to Ri. Next to so temperatures we can take here temperature T1, this is T2, this is T3, temperature hot fluid temperature THF, cold fluid temperature TCF, hot fluid heat transfer coefficient HHF, cold fluid heat transfer coefficient HCF. These are the values. So radiuses, the inner radius is equal to, you can take R1. Next to outer radius of the first layer R2, outer layer of the second layer, so this is the R3. So you can consider all this one, K1 and K2 thermal conductivity of the coaxial layers, layer A and layer B. Hot fluid temperature HHF, THF, and HHF is the heat transfer coefficient of hot fluid. TCF is the cold fluid temperature, and HCF is the heat transfer coefficient of cold fluid. Okay, so L is the length of the cylinder, Q is the rate of heat transfer. So if you apply the first rate of heat transfer in layer 1, just like you know the formula, 2 pi KL into T1 minus Ti minus T naught by ln R naught by Ri. So similarly, T1 is the initial temperature. Next to outer layer temperature is equal to T2. If you apply this one, you will get this one. T1 minus T2 is equal to Q by, so this value. So similarly, this is the second layer. There are two layers. The rate of heat transfer in the second layer. Okay. If you add this next in this one also, we have to consider. So heat transfer here conduction, here conduction, here convection, here convection. So convection formulas also you have to consider this one. Then this is the convection formula. Okay, HA into temperature difference, HA area is equal to 2 pi R3. Okay. If you add all these four equations, then we will get the final equation, that is the rate of heat transfer in composite cylinders. Okay, so 2 pi L into hot fluid temperature minus cold fluid temperature, initial temperature minus final temperature, by all the thermal resistances: convection thermal resistance, conduction thermal resistance, conduction thermal resistance, and convection thermal resistance. Okay, so in this way, just like you can, this is the final formula for the composite cylinders. Q is equal to initial temperature minus final temperature by all the thermal resistances. Okay, so in this way, just you can solve any type of composite cylinders, uh, heat transfer for the composite cylinders in many layers of cylinders. Okay. So these are the different textbooks. You can refer this for this topic. Thank you for listening to this class. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.